So, yeah, like, I think some of you might have seen the title before the talk. I had struck out riches and said, I'll tell a tale of rag to results. But then, as I started working on the presentation, I did some more strike-throughs. So it's not that I'm not going to talk about rag, which is basically retrieval augmented generation. But what I thought was, there is a plethora of techniques, actually, through which you can use LLMs on your own private data. So by private data, I mean both personal and enterprise data. So this talk will be like a landscape review of all those techniques. Again, this whole space is evolving too fast. So, whatever I could research, I've tried to present here, and I hope that during the Q&A sessions, if you have other ideas, you can share that as well. And I'll try to not throw jargon at you guys, and we'll try to go in a little more deeper in the 30 minutes. Of course, that's all that we have, but we'll try to make an attempt to understand a little more into each of the techniques and algorithms that we discuss. So let's start with the biggest question, right, in everybody's mind: humans versus LLM. So let's just quickly look at how humans operate, right? So we think, and then we speak, right? So there is a thought, and that is converted into language. And with LLMs, it is speak, speak, speak. Now I don't want to be like a class teacher trying to, bucket two categories of people. One, people who think and speak, and the other chatterboxes. Of course, we know that LLMs are far more powerful than most humans right now. But what do I mean when I say speak, speak, speak? Right? So, can you just play the video and then you can pause, yeah. So if you quickly, like, let's say you ask GPT, right, to tell yourself a bedtime story. You can stop here. Yeah, you can pause. You can pause. Yeah, you just pause it. Okay, yeah. So, you're at this point, right? Unlike a human who's narrating a story, the LLM actually doesn't know what the plot is, even at this point, right? It doesn't know what's going to happen at the end. All it's trying to do is, based on everything that was said by itself, as well as the prompt, it's going to predict that next one single token, right? And that is all that it predicts. All the computation that it does is to predict the next word, and the next word, and the next word, and that, to us, forms a thought. It's almost like the thought is in the human mind, whereas LLM is just spitting out language. But just because it has been trained on, trillions and trillions of data out there, right, across web and books and articles and stuff, right, what it churns out looks very, very meaningful to us, and it basically depicts things like idea, knowledge, concepts, imagination, everything, right? But it is all just language generation, right? So on that note, let's just quickly look at how LLMs. So what are LLMs, right? Let's start from there. Sorry, actually before that, right? Like, okay, this is how I think humans think, right? So now, I guess many of you in the room know what this thought is, right? But we don't start by saying this, right? Like, in our mind, we imagine losing our jobs to maybe LLMs, to next generation AI, and then we would articulate it in this way. Whereas for an LLM, it's all about giving out these tokens, which of course is meaningful, right, at the end of the day, right? So how do LLMs work? So LLMs are nothing but a giant neural network. So what is a neural network, right? So like every time we give a prompt, it's a sequence of words, right? So these words are mapped into some numbers. You can think of these numbers to be like an array, if you are a computer science student, or a vector, right? So that transformation, those vectors are called embeddings, but think of it as basically a sequence of numbers, right? So over here, what you see happening is, basically there is input x1 and x2, that gets transformed into another series of vectors or numbers, which is h1, h2, h3, which again gets transformed into another series of vectors, which is o1 and o2. And how does that transformation happen? So x1 and x2, right, the series of numbers, is getting multiplied by a matrix, WH, right? And then you get another matrix, which is the H matrix, which is again being multiplied by another matrix, W0. And then you get another matrix, which is the output matrix, right? So in essence, neural networks are essentially a mathematical function that involves a series of matrix multiplication, right? I mean, it is just a series of matrix multiplication. Of course, I am simplifying things a bit. In addition to matrix multiplications, there are a few more operations like matrix additions. There are biases that are added, and then there are some functions that act on vectors themselves, like softmax, etc., etc. But in a sense, right, I think the key takeaway I would say from this slide for the rest of the presentation is that whenever somebody says a neural network LLM, think of it as a series of matrix multiplications happening in the GPU, right, which will transform any input that you give into to an output set of numbers, again, which will be mapped back into words or image or video, right? And that is also through some matrix multiplications. Okay, so just, as you can see, these WH, W0, these are the weight matrices. And when somebody says we have a 80 billion parameter model, it is just each of these values in all these different matrices, right? So there are so many matrices out there. And if you count the number of elements in those matrices, put it together, that's 80 billion, right? And yeah. So LLMs, what are they? They are, of course, a type of a transformer, right? They're not a simple neural network as I showed in the previous slide, right? So what makes transformers different from typical neural networks, right? And you will see, actually they are very different, but let's look at what are transformers, right? As you all know, this technology of transformers was really pivotal to the progress of AI. Without transformers, I don't think all that has happened in the last few years, even with OpenAI, would have happened, but for this path-breaking research. So what are transformers? They are a set of encoders and decoders. And what do these encoders and decoders do? So encoders, basically they try to take the input, do some transformations, and while doing the transformation, they have something called as an attention mechanism, right? So what does that mean? So when you say a sentence, right, and you're trying to say the next sentence, the next word, right, the next word has some correlation to each of the words that you have stated previously, right? It tries to understand what is the importance of all the past words that were said when you're generating or when you're saying, we are humans, when you're speaking the next word, right? So that is encoders and decoders. And I told you that LLMs are just matrix multiplication machines, right? So now I think some of you might ask, where did the matrix multiplications disappear, right? So let's look at what is an encoder and what is a decoder. So encoders look like this. Like every encoder and a decoder has basically two sub-neural networks in it. One which is called the self-attention, the other which is basically feed-forward, right? Now, what do these modules actually mean? So let's first look at, as you can see, this basically transforms embeddings or vectors, which is a series of numbers, as I said, into another series of vectors, which will come out as output. So what is feed-forward? Feed-forward is actually a simple neural network, which is again just a series of matrix multiplication, which we saw on the previous slide, right? So there are weight matrices, which is multiplying the incoming input, transforming it into outputs. And what is self-attention, right? So self-attention, so all the magic that we see today actually lies in this single formula, right? Which actually transformed the way machines were able to interpret language, right? So you see that there are three key matrices here, Q, K, and V. So Q is the query matrix, K is the key matrix, and V is the value matrix. So again, I'm not going to go into the next level of detail, but suffices to say the following, right? Which is basically your input is transformed into a query. Every word that you give is transformed into a query vector, into an equivalent key vector, and an equivalent value vector. And again, now you can see that just like the previous, like a feed-forward network, you can see that self-attention is also a series of matrix multiplications, right? You're multiplying a matrix Q with K, applying a vector function, and then again multiplying it with V, right? And just before I go to the next slide, right? So the whole thing about attention dwells in that K matrix, the key matrix, which basically says how do how does a word's presence, how is it influenced by other words in a sentence? Like for example, if I want to say that John loves football and dash is playing it, right? He is playing it. So he is related to the word John, and similarly playing is related to the word football, right? So that interactions, that influence is actually captured by the K matrix, which is nothing but attention. So there is a paper, the path-breaking paper on this front. Attention is all you need. So if somebody is interested, you can read it. It's quite tough to read it. And there are, of course, some illustrations on the web which will help you to sort of get into the details of this. But the heart of it is just these three matrices, which again are getting multiplied by your input. Okay, so then for those people who are a little more inquisitive, this is basically the Llama 3 model, right? And we are not going to go into the details, but you can see that this has self-attention, feed-forward networks, etc., right? So this is how basically, whether it's OpenAI, Llama, or any other LLM that you're using, right, is going to have roughly a similar architecture when it transforms an input prompt into a sequence of output tokens. So, yeah, so now comes the most interesting question. So we know that LLMs are really powerful, they are omniscient. Now, how do we make these LLMs operate on our data? So what is our data? So personal data, right? So LLMs have been trained on web-wide data, but it still doesn't know any of our personal information. And it also doesn't know about enterprise data. So let's quickly look at examples where we could use, or can we, questions on, let's address questions on whether we can use LLMs on, like, let's say personal data, right? Like if you're going to go and ask any LLM today, right? Which of my friends have visited Scotland to guide me on my tour plan there, right? The LLMs are not going to be able to answer it because it's private data, it's personal data, right? Or what were my major expenses in my credit card statement last month, right? And basically, if a powerful LLM should be able to answer these questions too, right? In essence, act as your own personal assistant. Yeah.
Question?
Yes, please. Yeah.
So we were presenting a startup to one of these investors, and a lot of our work is, we pull dealer data from 2,000 plus dealer websites in the US, along with other websites, and that's sort of the starting point of our insights.
Yeah.
So this guy said the chat GPT will have all this information anyway, and of course we had a different opinion.
Yeah.
They don't pull all this data.
Yeah.
So what's your perspective?
Yeah.
How much of this data is part of your IP and how much
Yeah.
should be away? Throw some light on it.
Yeah. Yeah. So basically, right, LLMs will have knowledge-based data, right? But it's not going to have, dynamic data. Like for example, car sales happening this month. They will not have the data. They will not have anything that is, obviously, anything that is instant, anything happening around the world, LLMs are going to miss that data for sure. And also, it's not been trained on structured data too, right? A lot of the data comes from text as is, right? So there is scope to, look into structured data and then use the power of LLMs as well, right? So that's one example, which is where LLMs can still be used on seemingly public data. And again, if you look at enterprise data, right? Like I'm sure many of you are in startups, you switch companies, these are some of the questions you invariably would have asked once you change your company, right? Like, can I delay my paternal leave by 3 months? Right? Who is the go-to person to fix some issue? Or, what's the difference between V1 and V2 of this product? Right? Like, or how many offline marketing campaigns were done last month? LLMs obviously have no answer to it, but they have the ability to understand these questions and potentially, if you build it right, look into the right sources and give you answers to this data, right? So in the rest of the talk, we're going to look at how do we get LLMs to answer these questions, right?
Just one more question.
Yeah.
Now or later, tell us what LLMs can't do.
Yeah. Yeah, I think they'll do everything. Nobody's job is safe. Okay, so how do we get LLMs to know about this data, right? Like the first and foremost thought, I'm sure in everybody's mind, is fine-tuning, right? Like you can fine-tune an LLM and make it aware of this data. So let's quickly look at what fine-tuning means, right? So fine-tuning is simple. So if you have an open source language model like Llama 3, right? Then you have it already, and then you can bring in your own data sets and basically train it further, right? So in essence over here, fine tuning is nothing but training. It's the fine tuning looks like a fine word, but all that you're doing is they've already trained and given you a model. Now you take that model and then you give more training data to it, and you're training it further. That is all that you do if you go with this option of full fine tuning, right? So what's going to happen? Like remember I said that LLM is a series of matrix multiplications. There are n number of matrices within an LLM. So all those matrices are going to be updated as you do the training, right? So for example, if your model is 175 billion parameters, after you do your one round of training, you are now left with 175 billion new values, right? But then this LLM knows everything about your data. It's your private little assistant, so it can answer questions about your own data, right? But then it is as big as a model as the original model, right? So now, what are the challenges going with this approach? Right, so basically, right, so the weight matrix is completely replaced. The old weight matrix is no longer relevant. So what you need to do is now you need to host this new set of weight matrices in the cloud yourself, right? So you cannot use a shared LLM. Like for example, you cannot use an OpenAI LLM if you're going to do full fine tuning, right? So you have to host the LLM, which means that you will incur GPU cost to keep it running all the time. So there are cost implications when you go ahead with a full fine tuning approach, right? I'm not saying that it cannot be used. There are circumstances where you will want to use it. You know, when it's strictly private data, you don't want it to escape. You can still do, you know, full fine tuning, right? Again, it is basically a function of the budget that you have. The second problem over here is overfitting, right? Overfitting is what if the LLM forgets the past? You gave it so much data. Now it only remembers what you say. It knows nothing from outside the world, right? And then that's not good either, right? Like the reason for you to start from a pre-trained LLM is you don't want the LLM to actually forget things. You want it to both retain the past and the present. But that's not how it works because it's updating the same set of matrices, right? And the third thing, and this is the biggest challenge right now with using any LLM, right? I think how many of you are, these days go to LLM to get, like, I've replaced Google with LLMs. Wow, that's a pretty big number, right? So I still go to Google. One is for, like I said, like real-time information, and the second is, it hallucinates. Like, I actually, like somebody told me, like there is this, I'm not a Mallu, but somebody told me about a Mohanlal and Shobana movie, and they told a sequence, and I asked the LLM, and it said something, and I just told it to my my friend, and he said, no, this is all bullshit. And such a sequence never happens in the movie. But basically, the LLM was just generating its own screenplay and story sequence for a Malayalam movie, right? So that's how smart it is, but it's not giving the information that you want, right? So hallucinations are a big problem with LLMs, and the problem of hallucination doesn't go away even if you train with your private data, right? And typically, when you're training with private data, like one thing you want is accuracy, right? You don't want LLM to give you general fundas, but LLM will give you general fundas back again, right? And sometimes that is plain wrong. So that's the problem with hallucination. So this is the approach. These are the pros and cons, I would say, with full fine tuning. So what is the next option? So the next option is something called as PEFT. Like, don't get frightened by the jargon there, parameter efficient fine tuning. It's actually quite simple. So there is this technique called LoRa. Okay. So now remember I said that we are going to change this W matrix, the weight matrix, completely with another matrix, W dash, right? So what is going to happen is W is actually going to become W dash, which means that I have to add something to W, right? Some delta W I have to add, which has the differences, so that I can get W dash. So I think there is a problem in the in PowerPoint. I did it on Google Slides. So that's a triangle there, which has become a rectangle in Microsoft's PowerPoint. I'm an ex-Googler. So that's delta W. So delta W is the difference between Yeah, the matrices are rectangular, but yeah. Delta W is basically a difference between the weight matrix that you currently have and the weight matrix that you're going to have after you do the fine tuning, right? So if W is a matrix of size D into K, obviously delta W is also D into K, right? So currently you're going to train 175 billion, find 175 billion new values, except if you do the following, right? So basically, if you all remember your matrix multiplication from your college days or +2 days, right? So if you have a matrix D by K, right, it can be actually factorized into two matrices, one of size D into 1, and the other is 1 into R, right? So if you multiply a D cross 1 matrix with a 1 cross R matrix, the resulting matrix would be D cross K, right? So essentially, instead of trying to find D into K values, you try to find D into 1 values, which is D values, and K into 1 value, right? So you have basically reduced from D into K to D plus K. And that's a big, big improvement, right? And this works if you can find such matrices, right? A and B, if you multiply, and you will get the actual delta W. That's not going to happen, but still we'll go ahead and find A and B. And it is going to be a little bit error prone. It's going to be approximate, but the beauty is that it works, right? So it works because if you remember, one of the problems in the previous method was overfitting, okay? So if you are not too accurate, then you will remember the past and you will remember the future. So it's almost like don't pay too much attention to what is happening now, and you will end up in a situation where you try to remember the past and the present, right? I mean, this is a little different kind of attention though. Okay, so what has magically happened is, instead of changing 175 billion values, now you have changed only like these new values just account to 17.5 million parameters. So that is an order of 10,000 improvement, right? And this is the reason why companies like OpenAI say, we'll provide fine tuning and we'll host it on the cloud for you. Because they will have one massive shared LLM with the 175 billion parameters or whatever parameters that GPT-4 or 4 Turbo or whatever they have, right, has. And for each one of your instances, they'll just store this 17.5 million values. And they'll pull it, they'll multiply, they pull it. I mean, like the multiplication, the way it will happen is your input vector will be multiplied by, this side, I should remember that. So the input matrix over here would be multiplied W as before. On the other side, it will be first multiplied by A, then by B, and then it will be concatenated. Okay, so this allows them to host many fine-tuned LLMs for different enterprises, different instances, right? So now let's look at, I haven't talked of QLoRa, I'll get there. Okay, sorry. Yeah, so as you can see, we have solved one problem, which is overfitting. It is faster tuning. I'm not sure, but okay, we'll go with that. I'm not sure it's faster tuning, but it is definitely lesser memory footprint, right? It's order of 10,000, we saw that. So if you have constraints on GPU, which I'm sure everybody in this room has, right? I don't know, is anyone from Google? OpenAI? Oh, one person from Google, okay. You just skip this slide, okay. Okay, so I think you'll have to go with LoRa. And there is an improvement on LoRa called QLoRa, which is basically quantized LoRa. And again, quantized LoRa is basically, there's nothing to do with machine learning. You can read that paper if you get, hallucinated by machine learning papers. But basically, it is quantization done on LoRa. They try to, actually, it's very interesting. As you know, right, all these weights are float numbers. And if you remember, float takes 4 bytes. Right, and with QLoRa, what they have done is they have tried to find, instead of 32-bit values, they try to find 4-bit values. 4-bit is almost like 0 to 16. What is there to find, right? But by quantization, they try to compute and find out 4-bit values, and they are able to get the same efficiency as LoRa. So it's interesting. You can go and read about it. But the biggest advantage is that now you can host it in the, you can use shared LLMs. right? You'll be paying some company there. But then the primary problem with hallucination still remains, right? So now we have covered 2 techniques. Let's go to the third one. Okay, so this is just like the three methods, right? Between that we saw so far: fine tuning, LoRa, and QLoRa. So you can see, right? Like if these are 16-bit transformers, so you can actually downsize it, make it 16-bit as well. But QLoRa goes one step further and transforms it into 4-bit and has the same efficiency and accuracy almost as LoRa. Okay, so now the third thing, right? Basically, right, like this makes fine-tuning just not necessary, right? If the context is very long. So what is context? Can anyone tell me what is context? Yeah, that's the size of the input prompt, right? And actually size of the output also, because if you remember in an LLM, the output tokens will get added back to input. Like LLM says everything based on what was said by the user and what it itself said. Like that's what we saw, right? So the context actually includes even the output. If you're going to ask it to generate a lot of text, don't use all that space for you to tell what it should do. Then you have to be precise if you want it to generate a lot of text. But basically the context length, for example, in GPT-4 Turbo is 128K. Okay. So if you have a few documents, like you have a few bank statements, you have like few Facebook, you have a few tweets, Facebook posts, and you want to have your own personal LLM, maybe, okay, so here you can see, right? With 128K, you can cover like 1,680 tweets on an average, or 123 Stack Overflows, or overflow questions. So the thing is, these context lengths are getting bigger and bigger, but the largest, I don't know who wrote this file. Does anyone know? Like Linux, I just came to know about this, that Linux has one file which is 514 to 128K. I don't know if it's even human readable anymore. Like, can somebody even touch that file? You'll have to leave it to LLMs, and you can't even give it as input on LLM, right? So yeah, so that's how big 128K is. If 128K was big, at least Google, this is again not out, maybe the Googlers in the room or the single Googler in the room can say, and Google claims that with their 1.5 Pro, they can take in 1 million tokens. There's one key difference here. This is not an LLM. Actually, it's a multimodal model. So it can take text tokens, it can take image, video, everything into it. But it can take 1 million tokens as your context length. And the example they've used is, they gave the input of, the air-to-ground voice transcription of Apollo 11, the moon landing mission, and then you can ask questions from it. Like, what did Neil Armstrong say just before he said, a small step for man is a giant leap for man? You could ask questions like that, and you'll get answers, right? So, which means that you don't need to do any fine-tuning, right? Now, so it all depends on how much data you have at hand. If your enterprise data is pretty big, then this is not going to work. And also the fact is, every time you're giving such a large input, right? So it's going to get slower, and it's going to be costly, right? Like OpenAI charges on tokens, so they'll make some money out of this. And but the good news is there is lesser hallucination. Like, why is there lesser hallucination? Because now the question that you're asking is a comprehension question, right? That we all answered in school, right? We always wanted exams to become open book. Give me the book and then ask the questions, right? So that's exactly what we have done. So that we as students wouldn't have hallucinated back then. But so we are trying to do the same to LLMs, right? But the fact of the matter is, if you look at what is currently state of the art, being used, right? Even OpenAI's GPT-4, its context window is 4K, I think, 4K or 8K, I forget. But Llama 3 is also 8K, right? So the context windows currently are still smaller, right? So they may not work. But this is also progressing at the same time. Like, we need to be aware of it, right? And then comes to the actual topic that I wanted to talk about earlier, which was RAG, which is Retrieval Augmented Generation, right? So I'm sure, like, how many of you are doing some sort of RAG in your own companies? Like, how many of you are not doing RAG? Please put your hands up. Okay, still, are you? Yeah, RAG is retrieval augmented generation. How many of you are not working on LLMs? Okay, good. Yeah. You trying to save your jobs. Yeah, I think nobody should work on it. But anyways, with RAG, RAG is basically a two-pass algorithm, right? So what do you do with RAG? If somebody asks you a question, right, then instead of directly giving it to LLM, what you do is you try to find a few documents, maybe 4 or 5 documents, again, comprehension method, and give it to the LLM and say, now please answer from these documents, right? So can I delay my paternity leave with RAG? What will you do? You will retrieve like maybe 5 leave policy documents or all the leave policy documents. Hopefully it's small, smaller than the 8K context window. And then ask the question, can I delay my paternity leave or maternity leave? Oh no, maternity can't, paternity leave. So then the answer is, the LLM will be able to answer better because the answer is somewhere in that document, right? So this is RAG. And what are the pros and cons of RAG? Right, the pro is that lesser hallucination, right? Because it's an open book question. And you can work with small contexts and there is no fine-tuning requirement. But the cons is, what is the biggest, actually I showed the answer, but what's the biggest challenge like whoever is working on RAG is facing? Somebody can answer that. Yeah. Yeah, getting the right documents. Anything else? Yeah, that's it. That's the only problem actually. Latency is also a problem. Yes, agreed. So, because you're now doing 2-pass as well, right? So, if you're slow in retrieving, it's going to be slow as well, right? So, how do you get the right documents? And of course, you need to build an extra system.
The question is, those documents you provided for extra context, would that enrich the overall learning?
So like unlike humans, right? If somebody asks us a question, right? When you guys ask a question, hopefully I'm learning, not sure, but hopefully all of us try to learn. But with LLMs, the way they are implemented, they only answer questions, they don't learn. But maybe behind the scenes, these companies might take our questions and train them. I mean, they may be aggregated, anonymized, done whatever. I'm sure it's learning, but not immediately, right? I mean, it also prevents from somebody, sort of spreading fake news through LLMs, right? You tell the LLM, okay, this is the truth from now on, right? You don't want it to be reflected in the LLM's weights as well, right? So it's not happening that way. Okay, so retrieval has to be accurate, and you need to get the documents within those top K. And the second part is, you still need an extra implementation. Like you need to have a system for RAG, right? You need to bring in vector databases. You need to decide what is the algorithm to use, etc., right? So let's look at the retrieval part, right? So this is a little naive methodology, right? Actually, before that, right? What do you guys, people who raise the hands for RAG, like what do you use for RAG? Okay, please go ahead.
How do you ensure that the corpus is good enough for the RAG?
The corpus. So this is enterprise data, right? If your HR did not write that leave policy document, that's it. Yeah.
We do have this challenge of hallucination with LLMs, right?
Yeah.
Plus, like we have a limited amount of corpus, or we are doing the testing, right?
Yeah.
In this case, maybe there is no policy related to paternity leave,
Yeah.
right? How do we ensure that it does not hallucinate if
Yeah.
there is no policy? Is it more on temperature control, or do you do something else on top of it?
Yeah, like you have to basically put it in the prompt as well. Please do not answer out of this book.
So
right?
basically temperature control then.
Yeah.
But are there any testing techniques as well that make sure that you have the required amount of RAG?
Yeah, actually, like I do not know. I mean, I have to try. Like, can we ask it to actually quote words before and after where it found this information? I don't know whether LLM does it. I haven't tried it. I'm just saying something on the fly. Then, if it can give some evidence, then we can go back and check. Yeah, so basically the question is, what if it doesn't answer from that? Like, you can ask it how many times, but... Yeah, so if it can refer to, just like we used to do in our comprehension questions, right? Like lines 1 to 5. If LLMs can do it, if it is trained that way, then there may be some hope there. Okay. Okay. Yeah. So.
The retrieve text and the hallucination part, it tests multiple things. So after you are creating a RAG pipeline, you can use that tool to like test the pipeline,
Yeah.
which one is working and which one
Yeah.
is not working. So
Hopefully that LLM is not hallucinating.
yeah,
Yeah.
it's
Like,
called.
I mean, like you ask more people, right? Like even if people hallucinate, you ask more people. Hopefully, majority is not hallucinating. That's the key idea there. So anyway, so. This is the age-old technique. Like, okay, actually, I wanted to ask, like, what's the like? Someone can tell me what RAG technique they use? Yeah, just go ahead. Yeah.
Hi. So we started with a naive RAG where
yeah.
we were simply using similarity search from a vector database.
Yeah.
But we have built a tool which iterates through all possible retrieval mechanisms and spits out what is the best
Got it, yeah.
mechanism.
Yeah, so like the older technique used to be like trying to retrieve using text, right, from text search indices, right? And again, these were the problems, right? Text match, keywords will be missing, people use synonyms, spelling errors, semantic understanding is not there. I mean, you can still do this as an augmentation to the following, right, which is actually the embeddings themselves, right? So embeddings, what are embeddings? Embeddings are actually nothing but, like, as I said it's all matrix multiplications. How did word get converted into a vector? Because of embeddings, right? Embeddings are nothing but an n-dimensional point with which you represent every word, right? So, so you can see here, if you look at these embeddings, you can see that the embeddings are in such a way, like there are two key aspects you can see with embeddings. And the first one is that, words that represent the same concept are together. Like all the countries are red, they're all somewhere near in that space. Similarly, all the things in, like suggestion, calling, I mean, like you can see, like there is basically spatial locality, right? Like things on the same concepts are nearer to each other, right? And then the other part is very interesting. This was, again, I think one big advance with the whole evolution of LLMs is how these embeddings were formed, right? Like you can see that, like they took the embedding of man and they took the embedding of royal and they added man plus royal. And like vector algebra, like they got the embedding of king, okay? And then woman plus royal became queen. Right? I mean, this just naturally happened through training. Okay, and I think that has played a very big role because this means that the vector representations are actually, encoding the meaning of those words. Right? So before that, the embeddings used to be very poor. Like, anyway, so the embeddings approach is simple, right? Like you convert all the documents to embeddings, and basically, when I say documents, typically you have to split it into smaller paragraphs if the document is too long, right? A few sentences per document, I would say. And then you generate embeddings for each paragraph, right? From now on, I'll refer to paragraph embeddings as document embeddings itself. So the paragraph is essentially the document we would supply to the LLM if relevant, right? And then we convert the query also to an embedding vector, and then we try to match the query embedding to the document embeddings, right? So that is the vector search. So you can find there are multiple techniques between 2 points in space, right? This is the n-dimensional points, you can't imagine, but assume everything is 3-dimensional, there's a point here. Now you can find how close they are through primarily two techniques. One is Euclidean distance, is actual distance, or through basically cosine similarity. Like, it's simply put, it's like the angle from the origin, right? Are they lying exactly in the same direction or not, right? Like so mostly people use dot products, right? So I have 1.5 minutes left. Is that it? This is strictly 1.5? Okay. Okay, so there is, I have no, like I just try to copy paste, what are the different implementation approaches out there. There are a lot. Okay, so I let me just quickly go over some of the techniques here, like what happens behind the scenes. Even if you use any of these, right, they will ask you to select, for example, a nearest neighbor algorithm, right? Like how do you select it? First thing is what is called as dimensionality reduction, right? So now if you're going to compare, like BERT embedding is 768 values long, right? And you have to match it with all these document embeddings which are again 768 floats long, right? So now how do you do it? So basically, right, the idea is like when you reduce dimension, right? Like for example, this is in 3D. You'll find that all the same colored cubes are still coming closer to each other roughly in 2 dimension, and even also roughly in 1 dimension, right? But again, the lower and lower you go in dimension, obviously you're going to get errors, right? So it's the same technique which we do with dimensionality reduction. So I would have asked you guys, I have 15 seconds left, but so how do I basically reduce dimension? Okay, so take a matrix, okay, the matrix multiplication again, and fill it with random values, okay, totally random values. Just multiply and get an embedding. Now you get a smaller thing. Now if 2 values were roughly the same, the multiplication also will give the same. Very simple technique, it works. Now if you have like 5 values, right, you can compare against 10,000 different embeddings too, right? This is the simplest form of dimensionality reduction. There are other techniques like, like SVD, PCA, blah, blah, blah. As time is up. Okay. So I'm going fast.
You can take more 5 more minutes.
Okay, thank you so much. Okay. So this, I think everybody understood really quickly. And next technique is hierarchical navigable small words. This is very popular actually. Okay, this is like routing on the internet. Like you want to ping, like right now if you are sending a packet, like you ping google.com, you know that what's going to happen is, yeah, at some point you'll leave your LAN, you'll reach your ISP, then the packet is jumping from one ISP to another to ISP, right? It's going to go across transocean cables and stuff, right? Like this is like going across like the bigger routers, then it comes to the smaller routers, then the smallest routers, hub, Wi-Fi, then your laptop, right? So this is how routing happens. I say this is an ex-network engineer from Cisco. So, so you can't question me. So here you see, right? Like, so now how does it translate into the vector world, right? So suppose this black dot, right, is what you're trying to search. Okay. So these are like these long distance routers, okay. So basically you first start here, you find it's too far, you go here, too far, you come here, you say, oh, okay, this is nearer. Then you go to the next level. So you've now switched from a long distance router into like this, you can say this is WAN, this is somewhat like a MAN, whatever that is, right? So from here, right, again you see this point, right? So you go in this direction, you go in this direction, you see this is the nearest. Then now you're going to go into your LAN, you go here, and then you go here and say this is the closest, right? This is like a routing algorithm. So take your document embeddings. If you use this algorithm, the algorithm will create this sort of routing table for you, right? So I've completed this. Okay, so the problem here, it's greedy. Okay, somewhere you can get stuck actually. So it's prone to errors, but it works well most of the times, right? So, and then this is again a very popular approach, right? So instead of comparing with every single vector, you cluster the points, right? So these points are now in 3 partitions. Now instead of comparing with every point, first you compare with the centroid, and you find if it's similar, then you compare with all the points within that cluster. Okay, so now it's all a matter of you finding a number of clusters and number of points you want to keep within every cluster, right? So that's the trade-off that you do. Okay, and this is going to be the last slide. So there are some advancements that Google has done on this. Okay, sorry, yeah. So what is the problem with clustering? It's not perfect, right? And documents that cluster boundaries can go to any cluster. So we may not end up checking the right partition. Okay, so if the point is like over here, right? And if we have a top 1, right, instead of top 2, then we'll check only here, and we are going to, because this was assigned here, we're going to miss this point totally, right, which might be the right document. Okay, so that's the problem. So Google came up with a very simple approach, but I don't know why nobody thought of it earlier. They have a paper on it, which basically they say that assign the document to multiple clusters. This is very simple, right? And also I think the second part is actually their key innovation, which is they assign it in a way to maximize dot product rather than Euclidean distance. Actually, yeah, I will not get into the detail right now because I have run out of time. But in essence, right, so the takeaway is that if you have your own data, right, so there are a bunch of techniques you can do. Like one is fine tuning with your own data, which when will you use it? When you have large, static, private content where accuracy is not that important, right? And then second is long context prompt. I think for most of us in this room, I'm assuming all of us are more in the application domain. We'll just have to wait for advances here. when long context become cheaper and faster. And the third is basically RAG, where there is little hallucination. There is no need for fine tuning, but you need to build the system, retrieval system. And finally, now the error has shifted from hallucination to your, your retrieval accuracy, right? So on that note, I'll end here. I'll just take 2 questions, from the audience. Thank you. Yeah.
So I had a quick question on the RAG optimization technique, right? So like I mentioned earlier, like we started out with a naive RAG, but what have you seen? Have you seen anything that people are using to find the most optimal document retrieval approach or the most advanced retrieval approach? What has been the approach to get to that? Yeah,
so I think mostly it is getting that embedding algorithm right. Like you can see different types of errors come from which type of approach that you are taking. Right? So the more the embeddings you compare with, the more the accuracy there is. The other alternate technique is also people sometimes use a mix of text search and embeddings. Like sometimes, just because those words were there, even if the embedding match did not happen, you can just throw that document also into the list of documents being passed into the LLM. So yeah, that is where humans still have some work.
So you just have to try each approach manually and iterate through.
Yeah. So this is a very typical search quality. I mean, like if you look at a search quality engineer at Google back in the day, now I don't know, they're just asking LLM to do everything and they're doing something else on the side. But back in the day, they used to tune these things. It was almost hand tuned. So I think this will be like a 3-month effort, at least at a minimum, right? If you want to get the kind of quality where the RAG doesn't say, I'm not sure, I don't know, right? Like if you want the answers, then you'll have to work on it.
Thank you.
Yes.
You said that like when we are using RAG, we don't need to do fine tuning. Yeah. But I think we can still use like fine tuning for reducing the hallucination and improving the results from the LLM.
Yeah, perfect. So like if you have your own corpus, very unique, like not a lot of that data doesn't reflect real world, or it probably augments it, right? I think the better the performance would be when you have both fine tuning done and documents. But the thing is, you're in your prompt, if you're going to say like don't go outside for answers, right? Just answer from these documents. And if you want the LLM to follow that, and the LLM really does that, then not sure how much fine tuning will help. But maybe if the answer, like alternate prompt would be like, if you don't find answers from here, just say from your knowledge.
Yeah,
right?
But smaller LLMs like 3.5 Turbo doesn't follow that when we do prompting.
Yeah, it doesn't follow.
That's a problem.
Yeah, GPT-4o also has issues. So, yeah, we just have to pay for it. Pay OpenAI. That's there. Yeah.
Yeah, that's where fine tuning comes to reduce that problem.
Sure. Yeah, like then the hallucination is still not solved with GPT 3.5, right? The hallucination problem still remains. Yeah. Any other questions?
Everybody's looking at me whether I'll allow it or not.
No. Just one question is allowed. Yes, please. Yes, we have implemented. Yeah. Eightfold is a company in the AI space. So we use AI for hiring. So very simply put, we try to match between people and jobs. So if you all apply to a company, your resume will get into the ATS and it will be forgotten by the recruiters. What Eightfold does is it looks at all the candidates sitting in the ATS, people who applied now, 6 months ago, a year ago, essentially people interested in the company, and then tries to rank them in the order of relevance for this newly posted opening, right? And how do we use? So we used deep learning techniques for this earlier. Now with LLMs, you can have more pointed questions also asked about different candidates, because now we have better understanding at a semantic level of resumes, jobs, job descriptions, so on and so forth. Yeah. So we use the embeddings approach, like at different levels, like resume, for example, resume itself can be converted to an embedding. Resume has different components. You have education, you have experience as multiple companies. Each of them can be an embedding itself, right? So yes, cool. Yeah. Thanks a lot, everyone, for this session. I learned a lot from you as well. Thank you so much.